we're going to continue our conversation about rigid body equilibrium by moving into 3D. The process for solving these problems is exactly the same as for 2D. We start with a free body diagram as our first step. Then we will move on to writing equilibrium equations and finally solve. But what's going to be new for us is these equilibrium equations. There will be a lot more of them, and they will probably take us a little more work to get written down. We will be summing forces in not just 2, but now 3 directions. We'll sum forces in the x, y, and the z direction. Those will all need to equal 0. And when we sum moments, instead of thinking about it as summing moments about a point, we will typically think of it as summing moments about axes. So we'll sum a moment about an x-axis, we will sum the moments about a y-axis, and some moments about the z-axis. We will be able to pick and choose which x-axis and which y-axis we use to make the math come out as easily as possible for that solving process. We will be able to write up to 6 equations for some problems, which means we may be needing to solve for 6 unknowns. We need to spend a couple of minutes talking about the different kinds of supports we'll have in 3D. As with 2D, we have several supports that will just lead to a single reaction force. And these are the same as you'll find in 2D. What's going to give rise to a single reaction force are things like cables, rollers, smooth supports. The next thing we have is kind of the 3D version of a pin. We call it a ball and socket. And the idea with a ball and socket is it allows free rotation about any axis, but does not allow translation in any direction. So we're going to have 3 unknown force components at a ball and socket. So we usually write those, if the ball and socket is at point A, we write those as AX, AY, and AZ. The next one I'm going to talk about is actually our most complicated. Sometimes we'll have a fully fixed support. And when we have a fully fixed support, it prevents all motion at that location. So that means that we will need to put on there, when we draw our free body diagram, all 3 force components, as well as all 3 moment components. So you'll have 6 unknowns. So both of these, 3 force components and 3 moment components, at a fixed support when it's a 3-dimensional problem. The final group I want to talk about are what we call bearings and hinges. And depending on the situation, you will typically have 2 to 3 force components and sometimes 2 moment components. Sometimes. Usually it's a support for a round shaft that is designed to allow that shaft to rotate about the axis of the shaft, but it's typically going to prevent it from moving up and down, prevent it from moving forward and backward. And then there are 2 terminology things that you're going to see show up in the book. One is what we call a thrust bearing, and the other is called a journal bearing. This is how we're going to decide whether we're going to put 2 versus 3 force components on our bearing. A journal bearing allows free sliding along the axis. So for a journal bearing, you will have no reaction force along the axis. A thrust bearing, you do. So you will include a reaction force along the axis. And that's the difference. That's how you know if at a bearing you're going to have 2 or 3 force components. It depends on whether it is a journal bearing or a thrust bearing. And we consider that force along the x-axis. It's sometimes called axial thrust. So if the bearing can support axial thrust and prevent the translation that would occur if you had a big force along the axis, it's called a thrust bearing. You'll put all 3 force components on a thrust bearing. Journal bearing, you assume it's free to slide this way, so you would only apply forces perpendicular to the axis for a journal bearing. As far as the moments, typically if we only have a single bearing, can you see how if somebody were trying to push down on one side and push up on the other, because this bearing has a finite width, it can prevent that rotation and produce a moment. However, oftentimes bearings are used in pairs or more. Like on my doors, I've got 3 hinges. Some doors have 2 hinges. Bearings are often in pairs. So what we assume is when we have 2 or more hinges or bearings, we neglect the reaction moments. And the reason we do this is, frankly, we would end up with too many unknowns. If you had 2 bearings and they each had a couple of force components and a couple of moment components, you're up to 8 unknowns and you won't be able to solve. You can only write 6 equations. So that's one of the reasons that we neglect them. But also, if you think about a door swinging on its hinges, you really don't want those hinges carrying a whole bunch of moment in a direction like this or this, because they will wear out really fast. So we typically want to align them very well. When we have 2 or more bearings or hinges, we only include the force pieces. If there's a single bearing or hinge, we will need to also include these moments. And I'll try to make that really clear in the problems that we work together as examples. So that's a really brief recap of the supports. Let's go and work as many examples as we can get through today. So this first example is kind of a warm-up example. It's a triangular plate that has a force P acting on it. We're told that P is 6 kilonewtons, and we're given the location by some coordinates, X and Y. And we are asked to find the tension developed in these 3 cables, and it says to neglect the weight of the plate. So our first step, as always, is our free body diagram. Start with a triangle. We're drawing a diagram of the plate. To draw this diagram, I removed all of the support cables. So I need to replace each of those cables with what they do to the plate. And they are all going to pull exactly up. These cables are oriented perfectly vertically in the Z direction. So all they can do is apply a force in that direction. And give these some names, maybe call it the tension in cable CD, tension in cable AB, and tension in cable EF. And then finally, there was a downward force, P, equal to 6 kilonewtons, somewhere off-centered in the plate. It's always helpful to kind of count up your unknowns. Looks like I have got a total of 3 unknowns. So I will need 3 equations to solve. Let's forge right ahead with writing our equilibrium equations. That is going to be our second step. If I start by summing forces in the X direction, has to add up to 0. Do you notice there are no forces in the X direction on this problem? So all I get from this equation is 0 equals 0. And the same thing happens if I try to sum forces in the Y direction. There are no forces in the Y direction. I get 0 equals 0. And that is part of why we don't have 6 unknowns. We have fewer unknowns because it turns out that some of these equations are not going to be very helpful for us when it comes time to solve. So let's finally get one that's not just 0 equals 0. Let's sum forces in the Z direction. Since I have some forces, let's decide if we want to call up or down positive for purposes of summing. And if I call up positive, I end up with tension in AB plus tension in CD plus tension in EF minus 6 kilonewtons equals 0. And it's a great equation, but it doesn't help me solve yet because it's got 3 unknowns in it. At this point, we've used up all of our force equations. Now we're going to have to sum moments about an axis. You can sum moments about any axis. I typically like to stick with axes that are in the X, Y, or Z direction because it makes finding perpendicular distances easier. And you want to try to pick an axis such as this X axis right here that goes through as many unknowns as possible. So this axis is a great option because it goes right through point E and point A. So those tensions in those 2 cables have a 0 distance away from the axis, so their moment will be 0. So I'll get an equation that only has 1 unknown in it, and I'll be able to solve for it. So we're going to start with summing moments about that X axis. Pick a sign convention. I usually use the right hand rule, have my thumb point toward positive X, and then my fingers curl around to tell me what way is a positive moment. Doing that, then my 6 kilonewton force is going to actually cause a negative moment. So I'll start this equation out with a minus 6 kilonewtons. And then I need the perpendicular distance from that 6 kilonewton force back to the x-axis. So that's that distance right there. Looking at my original diagram, the force is right there. The axis is back here. So this perpendicular distance will be y, which was given in the problem as 1 meter. 6 kilonewtons times 1 meter. That's one of the moments about the x-axis. And then the only other force that can cause a moment about the x-axis is this TCD, because it's out here to the right and going upward, is going to cause a positive moment according to the right-hand rule. So I will have plus TCD, and then I need its perpendicular distance away from the x-axis. So there's the x-axis, there's the force, perpendicular distance will be just this y distance right there, which is 2 meters. And that can be solved very quickly. We get that TCD is 3 kilonewtons in the direction that I drew it on my diagram. Next, let's sum moments at another axis. And the other axis that's pretty helpful for this problem is actually the y-axis that goes right through points A and C. Because even though we know TCD, it's always just helpful to have an axis that eliminates as many forces as possible from your moment equation. So this axis, TCD and TAB will not cause moments because they have a 0 distance away from that axis. But P, our 6 kilonewton force will cause a positive moment about the y-axis, and then this upward TEF will cause a negative moment about the y-axis. Summing moments out the y-axis is that way. I will first have that my 6 kilonewtons causes a positive moment, and now I need the distance from the y-axis. So it's a z force. The axis is in the y direction, so my distance, perpendicular distance, will need to be that x distance, which is 0.75 meters. And then in the other direction, I'll have minus TEF. That's the force over here, and its perpendicular distance from the y-axis will be 2 meters away. And solving, we get that TEF is 2.25 kilonewtons. Now I can go back to my force in the z equation, this one right here in purple, and I will get that TAB is equal to 0.75 kilonewtons. And we're all done. We just needed to use these 3 equations to solve for our 3 unknowns. We never used the summation of moments about the z equation. And if you notice, because in this problem, every force is in the z direction, remember, a force that's in the z direction does not cause rotation about the z-axis. It has to be perpendicular to the axis to cause rotation. Since these are all parallel to the z-axis, they do not cause any moments about the z-axis. So summing moments about the z would just give us 0 equals 0 and not be helpful. Let's try another example that's a little bit more involved. In this problem, we have a pair of bearings. This is how our book draws bearings. We're told that A is a thrust bearing and B is a journal bearing. So we're going to go back and remember that the thrust bearing will have 3 reaction forces and the journal bearing will only have 2. That's the difference between them. We're told that the crate is 75 kilograms, so we'll have a weight downward. And we're supposed to solve for the force F that the person has to pull with to hold the crate in equilibrium in this position. And then it also asks us to find the reaction forces at the bearings. So, no surprise, our first step is once again a free body diagram. And it does not have to be a great looking free body diagram. In fact, I'm just going to draw a stick figure free body diagram. We've got a shaft, then it goes down and it goes out kind of like so. And maybe I'll include kind of a wheel-like thing to indicate where my weight is going to act out here at the front. In drawing that free body diagram, I removed bearings. So at each bearing, I need to replace them with what they did to the part. A was a thrust bearing. So at A, we're going to have all 3 reaction forces. We'll have an AX, we'll have an AY, and we'll have an AZ. Then B was a journal bearing, which means there will be no reaction force along the axis because it's free to slide along that axis, but there will be reaction forces in the other 2 directions, which for this problem happens to be the X direction and the Z direction because the axis is lined up with the Y axis. Those are all of my reaction forces. And then I also need to put on here the weight of my crate. The weight will be the mass times acceleration due to gravity, 9.81 meters per second squared. And then finally, somebody is pulling with a force in the X direction, F, that we need to solve for. And I think those are all the forces on my object. So what I need to do next is make sure that I can solve this. So if I count up my number of unknowns, I've got AX, AY, and AZ. I've got BX and BZ, and I've got F. So I'm counting a total of 6 unknowns. So I should be able to solve. It will take all 6 equations, but I should be able to solve for all of them. Next step is equilibrium equation. It's completely up to you whether you like to do the force equations first, since they're a little easier to write. I actually prefer to try to start solving for things right up front because it makes me feel like I'm making a lot of progress. With a problem with 6 unknowns, usually if you want to start solving for things right away, you need to start by summing moments. For example, if I sum moments about the y-axis right down through the shaft, that y-axis goes right through point A and point B. So that means that all 5 of these unknowns will cause no moment about the y-axis, meaning I'll be able to get an equation that only has 1 unknown in it. So let's start with that. I'm going to start with summing moments about the y-axis. It's got to equal 0. Pick a sign convention. So we already established that none of the forces at A or B will cause a moment about the y-axis because their distance away is 0. But I think this weight will. And since it's over here and down, right-hand rule tells me that's going to be a positive moment. So my force will be mg. And now I need a perpendicular distance away from the axis. So here's where I go back to my original picture. The force seems to be applied right here, which means perpendicular distance from the y-axis. I'm looking for that length. And on my diagram, it looks like it's 0.1 meters. So times 0.1 meters. That's a positive moment. And then my force down here, because it's down and below, it tends to cause, if you looked at it from this axis right here, looking back that direction, it looks like it's causing a clockwise moment. It's the opposite direction of the moment caused by my weight. So we would call this a negative moment about the y-axis. Magnitude of the force is F, and now I need a perpendicular distance away. So the force is right here. The axis is straight above it. I need to go straight up in a perpendicular sense. So that distance looks like 0.2 meters. Let's substitute in the mass, which was 75 kilograms. G was 9.81 meters per second squared times 0.1 meters. If you want to bring it to the other side, that's equal to F times 0.2 meters. The meters will cancel, and kilograms times meters per second squared, that's a Newton. So I'll end up getting that the force you have to apply to hold this in equilibrium is 368 Newtons. And since it came out as a positive, it means that I do have the force drawn in the right direction on my original diagram. Why don't we sum moments about another axis? Since it turns out that I'm not going to make a whole lot of progress, even still summing forces in the x direction. I now know F, but I don't know BX or AX. So why don't we try summing moments at another axis, see if I can find some more of my forces with just one equation. Point A is looking like a good place to look for an axis. And why don't we try summing moments about the x-axis through point A? Since that axis goes right through point A, none of the forces at A will cause a moment. Also, any force in the x direction will not cause a moment about the x-axis because they're parallel. So the only two forces that will cause moments about that x-axis would be the weight times this perpendicular distance. That would cause a moment that direction. And BZ times its distance would cause a moment the opposite direction. Let's put those, write that down, get those numbers in there. So some moments of the x-axis, it's got to be equal to 0. The weight is actually going to cause a negative moment on the x-axis because if you start with your hand here, go that way and curl your right hand fingers down, your thumb is pointing back in the negative x direction. So we'll start with minus mg, and then I need a distance away. Looks like this perpendicular distance away from the x-axis is going to be 0.6 meters. So multiply that times 0.6 meters. And then the only other force that we decided would cause a moment about the x-axis is BZ. It's going to cause a positive moment about the x-axis. So plus BZ, and its distance away is from A. I got to go this way, take my perpendicular distance. So I'll have 0.6 plus 0.5. So this is times 1.1 meter equal to 0. Solving, we get that BZ comes out to be positive 401 newtons. The positive means I drew it in the right direction. It doesn't mean up or down. It means that the direction that I drew it on my diagram was correct. So in my case, it does mean up. Now that we found BZ, did you notice that BZ and AZ are the only two unknown forces in the Z direction? We just solved for one. So let's go sum forces in the Z direction. I think we can solve for another unknown with a force equation. We've got BZ that I just found plus AZ that I don't know. The only other Z force will be my weight. Minus mg is equal to 0. So solving for that, we end up getting that AZ comes out to be plus 334 newtons, which means I drew it in the right direction on my diagram. It does, in fact, act upward. We've got one more moment equation we can use that we haven't used yet. So why don't we use that and see if that'll help us get another one of our unknown. If we sum moments about the Z-axis right here, that's the axis we haven't summed about yet. I still want to go back through A. Even though I've solved for a couple of these forces at A now, I still want to go back to point A because it has the most things going on. So for something else with the Z-axis, the forces at A cause no moment. The weight and BZ are parallel to the Z-axis. So the only two forces that will cause moments are BX that way and F the same way. Both of them actually happen to cause negative moments about the Z-axis using our sign convention. So we're summing moments about the Z-axis equals 0. So that's our positive direction. We will end up with minus bx times how far away it is. Bx is right here, and that distance will be from A to B, 0.6 plus 0.5, it'll be 1.1 meters away. And also negative f times however far f is from point A. And it's the distance in a perpendicular sense. So if my z-axis is right here, and my f is right there, what I need is that total y distance. So I'm going to add up the 0.6, the 0.5, this little 0.1, that gets me to 1.2, and there's another little 0.1, gets me to 1.3. It does not matter for purposes of something that's at the z-axis how far down below the axis it is in the z direction. All that matters is from the z-axis out to f, what is that perpendicular distance? So we're just needing the summation of all those y distances, which is 1.3 meters equals 0. And solving, I get a negative for bx. Bx comes out to be negative 435 newtons, which means I drew it in the wrong direction on my diagram. It does not actually act in the positive x direction. It actually needs to act in the negative x direction. So you can report that answer either just by circling what you've got, or if you prefer to have your answers be positive, call this 435 newtons in the negative x direction with an arrow to indicate which way it acts. Then let some forces in the x to solve for our other x force. In my diagram, I've got ax, bx, and f all coming out in the positive direction. Ax plus bx plus f equals 0. Let's substitute those values in. I'll have ax, bx is actually minus 435 newtons. F is plus 368 newtons. So in solving for ax, then we're going to get a positive plus 67 newtons, which means it does act the way I drew it on my diagram. All right, we've used 3 moment equations and 2 force equations. Finally, we need to solve for ay. So let's sum forces in the y. That's the one equation I haven't done yet. Summing forces in the y, let's go look at our free body diagram. We've got ay, and every other force on there is in the x or the z direction. So our equation just becomes ay equals 0. Because that's the only force in the y direction. In solving this, I did not explicitly write down a cross product. Did you notice when I summed moments, I simply wrote down forces and then I went and looked on the diagram to find perpendicular distances. I find that to be fastest, especially when all of the forces are in the x, y, and z directions. Now, if I'd had a tension here that had an x, y, and z component, maybe it would have been faster to use cross products. So let me show you guys just a quick example using cross products. If you're not very comfortable with finding perpendicular distances and figuring out which is whether it's positive or negative. So let's say I wanted to sum moments about the x-axis through point A. Well, what we need to do then is write every single one of our forces inside of a cross product. So if you remember, when we do this, we write these using unit vectors on the first row, position vectors on the second row, and force vectors on the third row. That's kind of just your reminder of how we did this for a moment about an axis. So for that x-axis, let's see what it's going to look like. The first row needs to be a unit vector along the axis. Well, it's the x-axis, so the unit vector will be 1, 0, 0. So every one of these that we're going to sum up is going to have a 1, 0, 0 because we are summing moments about the x-axis. And they all have to add up to 0. And let's start with one of our forces, like all the forces at point B. Let's do all the forces at point B to start with. So at B, we've got an x component and a z component, and then we need to have a position vector that takes us from A to B. To do that, we start at A and we just go exactly in the y direction, 1.1 meters. So what this first cross product term would look like is 0, 1.1 meters, 0. There's the position vector that takes you from A to B. And now we need the force at B, which will be, there's an x component, no y component because it's a journal bearing, and then there's a z component. And then you can take that cross product to see what comes out of it. Next, we need to deal with that weight. The weight was in the z direction, 0, 0 minus mg. It was pointed straight down in z direction. Now we need a position vector that gets us from point A to that downward force. So to do that, we have to go 0.6 meters in the y direction and 0.1 meter in the x direction. So we put in here 0.1 meters, 0.6 meters, and then 0, because we didn't have to go up or down at all to get to that force. Finally, I'm not including here the moment that the forces at point A would cause about this x-axis, because I think you guys can realize that they are on the x-axis, they have no distance, so they shouldn't be in this equation. But F should, and F is pointed in the x direction. So we'll write the force in here as F 0, 0. And now we need a position vector that gets us from A to F. So to get from A to F, we had to go 0.6 plus 0.5 plus 0.1 plus 0.1. We had to go 1.3 meters in the y direction, and we have to go minus 0.2 meters in the z direction. 1.3 meters in the y and minus 0.2 meters in the z direction. You notice those cross products have a whole bunch of zeros in them. So you're not going to have a lot of non-zero numbers left when you're done. If you do this first cross product, the only piece that ends up being non-zero is the piece you get when you're multiplying the 1 times 1.1 times bz. So we end up with 1.1 meters times bz. This second term, the only thing that ends up being left when you multiply it is this very first term. It's going to be 1 times 0.6 meters times minus mg. So we've got plus 0.6 meters times minus mg. And then this last one, it turns out every single term when you multiply out the cross product is 0. So we just get that that's equal to 0. If you notice, that's exactly the same thing. This equation, 1.1 bz minus 0.6 mg, is right what I got up here, 1.1 bz minus 0.6 mg when I sum also the x-axis. So if this works well for you to find perpendicular distances and figure out if it's positive or negative, go for it this way. If this is difficult for you, please feel free to write it out using cross products and do this math. Here's the nice thing about this. This will work to get me the moment about the x-axis. Guess what needs to change if I want to find the moments about the y-axis through point A? All I do is I replace this top row with 0, 1, 0. And now I can find same exact, everything else is exactly the same in the cross product. The distances from A to B and from A to F and from A to the weight, they're exactly the same. You just change which axis you're summing moments about by changing that top row and then redo the cross product. All right, so there's an alternate way to help you find the moment equation.